When we're working with applications of mathematics, we often need to do calculations beyond the set of problems that we do in a theoretical setting. For instance, if you are designing furniture in a wood shop and you need to use some trigonometry in order to determine lengths of items to produce the results that you want, your angle measures aren't necessarily going to be things like pi over 4 or pi over 6, these very rare angle measures that we're actually able to calculate exact values of sine, cosine, tangent, and the other trig functions. So we enlist the use of the calculator. And the calculator can do things like, for instance, if we wanted to know the tangent of 35 degrees, all right? We trust that the calculator can do that and come up with the correct response for us. And then we can use that value in our particular application. But if you think for a second, how does the calculator actually come up with that number? Like, what's happening behind the scenes that allows us to come up with a value like this? All we have from our theoretical mathematics are ways of calculating exact values for very special angle measures. And that's just the trig functions. We then have functions like logarithms, square roots, and so forth. There's a lot of different types of functions. How do we go about calculating these? How do we come up with values for any input? Well, we're going to actually find out how that could be possible today. And that's one of the more exciting results that we come up with in Calc 2, and especially in terms of sequences and series altogether. Because you have to admit, students don't always find the topic of sequences and series as the most exciting thing, but it really builds into this right here, and I think that this is actually really exciting. I come from a computer science and programming background. If any of you do as well, you'll probably find this pretty exciting as well. If you're coming from an engineering background, you'll probably just accept that the calculator gives you the answer you want and move on. No problem. But let's take a look at this and really get an understanding of what's happening behind the scenes. So in previous sections, we looked at arctangent in a lot of detail. And we saw how there's a method that we could take arctangent and express it as an infinite polynomial. So we could do things with arctangent right now in order to calculate arctangent really at any input value. We have enough information to be able to do that. But that's really special for arctangent. And the reason is because arctangent just happened to have a derivative that is a rational function, which we were able to apply polynomial division to in order to come up with an infinite series that would allow us to integrate and come up with a infinite polynomial for the arctangent function. So how can we do this for other types of functions like logarithms or sine and cosine, for instance? And it turns out that we have an ability to do that for any function. As long as we know what the derivative of the original function looks like, we can differentiate it. We can absolutely come up with approximations for it. So here's what we're going to do. So we understand that first, for any function, no matter what kind of function we have, the derivative gives us the slope of a line that best approximates the slope of the curve of that function at that particular point. So in effect, what we say there is that the slope of a curve at a given point linearizes the curve at that point. Okay? So when we say it linearizes, it gives us the best linear approximation to the curve at that particular point. So That's basically a degree 1 approximation, or we call that also a first order approximation. And it can be centered at specific points. It doesn't have to just be at 0, but it can be really anywhere. But we can improve on that. So instead of using a first order approximation, which is linear, we can actually use a second derivative and come up with a second order approximation. And that would be taking into effect the concavity. And really, if you can get a second derivative, you can get a third derivative, and a fourth, and a fifth. And I know that we generally don't have a lot of applications for derivatives beyond 2, but here we can get better and better approximations to a specific curve using higher order derivatives. And that's exactly what we do in the process of finding what's known as a Taylor series. So a Taylor series says that if a function f has n derivatives at a point x equals c, then, and I know this formula looks intimidating, but we'll parse through it here. The nth order approximation is given to us by the function evaluated at c plus the first derivative evaluated at c times x minus c plus the second derivative evaluated at c over 2 factorial times x minus c squared, and then this generalizes to the nth factorial evaluated at c over n factorial times x minus c to the nth power. And that right there is known as the nth order Taylor polynomial for a function centered at a point c. And generally speaking, I tend to focus on this nth term here and think of this as a formula. And you can kind of see where everything comes from. So x minus c, this part right here, tells us that we're centering the polynomial around the point c. That's all that's going on there. F to the n, or not f to the n, I'll just say it as the nth derivative of f. We're just getting increasing derivatives at that point. So first derivative, second derivative, third derivative, and so forth, and then evaluating at that particular point. The n factorial might be surprising, but what is happening there is, like, if you have x to the n, for instance, and you take a derivative of it, so I take the first derivative, then it would be n times x to the n minus 1. And then if I take a second derivative, then it would be n times n minus 1 x to the n minus 2. And if I take a third derivative, it would be n times n minus 1, whoops, not x, n minus 1 times n minus 2 x to the n minus 3. So these successive derivatives result in multipliers like this. But these multipliers, let's say we actually had a value for n. Let's say the value of n was 5. Okay, so if n is 5, this would be 5x to the 4th. And then this would be 5 times 4, because n 5 minus 1 would be 4, raised to the n minus 2, which would be 3. And then we would have 5 times 4 times 3, x to the second, and so forth. You can kind of see these multiplying constants here. If you know anything about the factorial function, you can see that that's kind of where this idea is coming from. So that's why the factorial's in the denominator, or at least an idea of why that's there. In this first example, we want to find a fourth order Taylor polynomial for the natural log of x centered at x equals 1. Then we're going to find a Taylor series for the natural log of x centered at x equals 1 and determine its interval of convergence. Okay, so let's think about the terminology here. So the Taylor polynomial is essentially a finite polynomial, so it has a finite number of terms. All right, the Taylor series is an infinite long polynomial. So we have essentially to find the nth term and define this as a series in series notation in order to come up with the Taylor series based off of the nth term of the Taylor polynomial. I'll show as we get to that point, but hopefully that makes sense. The interval of convergence, once you have a series, you can use the ratio test to determine an interval of convergence. So let's take a look at coming up with a Taylor polynomial for the natural log of x and see what we can do. Okay, so as I mentioned, I like to focus on this formula here, the nth term, and come up with first the coefficient on that, and then multiply by the polynomial part in the end. So I'll set up a table. We're looking for a fourth order approximation, so that's going to be where n goes up to 4. So I'm going to start my table going from 0, 1, 2, 3, and 4. Then the first thing I'm going to do is come up with the nth derivatives of each of those. So the 0th derivative, that's just going to be the original function, so natural log of x there. That's fine. The first derivative of natural log of x we know to be 1 over x. The second derivative, what we need to do there is just kind of course, rewrite the first derivative as x to the negative 1. When we differentiate this, we bring the exponent down and subtract 1 from that exponent. So that's to the negative second power. Or I could write it as negative 1 over x squared. The third derivative, I kind of just do the same thing. Negative x to the negative second, write it that way. Bring the negative 2 down, so that becomes 2 times x to the negative third. So this is going to be 2 over x to the third. And then there's kind of a pattern there that sort of emerges. So this next derivative, we bring the, 2x to the negative third. Bring the negative 3 down, so negative 3 times 2 would be negative 6x to the negative fourth. So negative 6 over x to the negative fourth. Okay, and that's just kind of getting some individual derivatives here. I probably should have put this over to the side a bit more, but the next part of my table here, a little space in between, the next part of my table, I want to evaluate each of those at c. And c is the value 1. So actually, I'll just change that to a 1. So evaluating the natural log at 1, so natural log of 1 we know to be 0. 1 over 1 is just 1. And then we would have negative 1 over x squared, so negative 1. 2 over 1, which is 2. And then negative 6 over 1, which would be negative 6. And I wrote that as to the negative fourth power, but of course that would have become positive in the denominator, so try and fix that there. Okay, the next part is to divide by n factorial. So in the next column of this table, I will take the nth derivative evaluated at 1, which is just the previous column, and divide that by n factorial. All right, so the nth column divided by n factorial. So that's just as effectively, the 0 factorial is defined to be 1, so 0 over 1 is 0. Then this column divided by 1 factorial, so that's 1 over 1, which is 1. Then negative 1 over 2 factorial, that would be negative 1/2. And then 2 divided by 3 factorial, essentially that would be 2 over 6, which is 1/3. And then negative 6 over 4 factorial would be negative 6 over 24. 6 goes into 24 4 times, so negative 1/4. Okay, so then I now have the coefficients. So this part of the Taylor polynomial, I need now this polynomial piece, which is really easy to do. They all just look like x minus 1 to increasing powers of n. So I really don't even do a different column for this table. I just now come up with the approximating polynomial. So I'll say p sub 4, so the approximating polynomial of the fourth order, is going to be this coefficient times x minus 1 to the nth power, plus this next coefficient times x minus 1 to the first power, plus this next coefficient, so minus 1/2, times x minus 1 to the second power, and so forth. So then plus 1/3 x minus 1 to the third power, minus 1/4 x minus 1 to the fourth power. Or simplifying, the first term goes away, second term becomes just x minus 1. Then I'll just write this one as x minus 1 squared over 2 plus x minus 1 to the third over 3 minus x minus 1 to the fourth over 4. All right, and there is my approximating polynomial with 4 terms. So that's the first part of this problem. So if I wanted to use this to calculate the natural logarithm at a specific value, I could do that. I could get an approximation. The calculator itself, if I plug in the natural log of 2, would give me the value here. But ultimately, there's an approximating polynomial inside the calculator, which is doing this. So, and if I use this approximating polynomial to find out what approximately the natural log of 2 is based off of it, here's what would happen. So 2 minus 1, I'm just plugging in for x, would just be 1. The next term would be 1 minus 1, which is 1 squared over 2, so minus 1/2. 2 minus 1 is 1, 1 cubed is still 1, so plus 1/3. And then minus 1/4. And then this value is not quite very close, but if I had enough terms, if I kept adding terms, that approximation would get better and better and better, ultimately leading to the value of 0.6931, for instance. But that's the idea. All right, so the Taylor series then for the natural log, we come up with an infinite series that pretty much represents the nth term of this polynomial. So in this case, it would be from n equals 1, I could start with, to infinity. The terms alternate in sign, so I need to put an alternating term in there, so -1 to the n, but that would start with negative to begin with, so let's do n plus 1. So we start with a positive. And then each term has a factor that looks like x minus 1 to the nth power. Then if we look at the denominators, if you'll notice, it's really just a pattern of 1, 2, 3, 4, so it's really just over n. So this right here represents a function that could produce every single polynomial term. So this approximation I did in the calculator, I could easily come up with what the next term would be. So like if I took that value and added the next term, which would be 1/5, then I get, a slightly better approximation. If I subtract the term after that, it's going to eventually lead us to this particular number. And ultimately, that's how calculators come up with these values. There's probably, for different functions, different optimizations that converge faster, but I would dare say that they all rely on approximating polynomials in some way. So, convergence. Let's look at the convergence of this series. So when it comes to convergence, we of course want to use the ratio test. The ratio test we do a limit as n goes to infinity for the nth term here. So we're doing absolute value, so the alternating term goes away. And then we do the n plus 1 term over the nth term. But the nth term here, it's instead of dividing by the nth term, it's easier, of course, to multiply by the inverse of the nth term. Okay. In evaluating this limit, x minus 1 to the n plus 1 could be written as x minus 1 to the n times x minus 1 all over n plus 1. And then this hasn't changed. What's nice about doing that is the nth x minus 1 to the nth power cancels in the numerator and the denominator. X minus 1, that factor can come out as a multiplier since it's not changing with respect to the variable n. So it's that times the limit as n goes to infinity of n over n plus 1. And then by rules of exponents here, rules of rational functions, this infinite limit, the degrees are the same, and therefore this would go to positive 1. So this whole limit goes to 1. So we have absolute value of x minus 1, which would converge whenever that's less than 1. So that tells me I have negative 1 less than x minus 1 less than 1, or if I add 1 to both sides, this is going to converge between 0 and 2, it looks like. Sorry about that. Of course, 1 plus 1 would be 2. We don't know what happens exactly at the endpoints. We would then have to test the endpoints. So at the endpoints, I have x equals 0. And if I plug that into my series over here, for x equals 0, this would be the sum from n equals 1 to infinity, negative 1 to the n plus 1. 0 minus 1 would be negative 1 to the n, all over n. So let's see how this reduces. This would be the series n equals 1 to infinity. Essentially, negative 1 to the n times negative 1. That could decompose into that. And the nice thing of doing that is these terms are in steps, so they cancel out. So then we have n equals 1 to infinity of negative 1 over n. And since we got negative 1 over n, it kind of looks like the alternating harmonic series, but it's not, because that would have to be negative 1 to the n over n. So it's not actually an alternating series. You can really just pull out that negative, and so this is the negative of the harmonic series. And the harmonic series diverges, so that means this series would also diverge. Okay, so what happens at 2? Well, we plug in x equals 2. We still have this term, negative 1 to the n plus 1. Then 2 minus 1 would be 1, so 1 to the n over n. Okay, then let's see, 1 to the n is just 1. Then we have essentially negative 1 to the n times negative 1 over n. So I can pull a negative out, and that would leave me negative 1 to the n over n. So this is the alternating harmonic series. It's getting negated But I think that's okay. It's just going to flip-flop the terms from each term from positive to negative. That's not going to affect the convergence of it. And we've already proven that the alternating harmonic series converges. So therefore, this series would converge as well. So that means the interval of convergence here is going to be 0 to 2, like this. So now I want to take a look at this and just make sure, we have a full visual understanding of what we just learned here. So let me pull that up. Okay, so I have here the curve in blue is, of course, the natural log function. And then the green line here is the first order approximation. And that's going to be just where it converges, so at 0 at the center point. Now, each individual term will be produced using this formula down here. If you note it is slightly different from the one that we were just looking at. This is the Taylor series for the natural log of 1 plus x. So essentially, you make a quick substitution. This would turn into x minus 1 to the n, and you'd have the exact same series. So we made it for the natural log of x. This one was produced for natural log of 1 plus x. No problem, we'll get the same results. All right, so if we add a term here to our approximating polynomial, we can see at positive 1, we get a really nice level of approximation within a small range here. All right, and that's just for a first order. If we go to the next term, then we get a quadratic, and this quadratic does a slightly better job, so it converges for a few more values. If we continue to add polynomial terms, if you'll notice, we get better and better approximations, but it doesn't look like those approximations go much further beyond say like a small range, and that range is what we came up with. So it's not going to converge at 0, which should make sense because the natural log has an asymptote at 0. It will converge at 2, we definitely saw that. And that's kind of what I was doing in the calculator. But actually we can look at the approximation. All right, and let me slide this over. Okay, so if I use an approximation close to 2, but not exactly 2, you can see that the approximation is actually much faster before 2, but it will work at 2 as long as we continue to add additional terms. And sorry, that gets overlapped there. Here I have 16 terms, and the approximation is accurate to 2 decimal places. So it converges pretty slowly, but eventually it does converge. If I go outside of the convergence, the interval of convergence, it diverges quite rapidly. So you can see that the approximation at 2.5, the actual natural log function is 0.918. The approximation here is 75. So it gets pretty bad outside of that range from 0 to 2. So that's why the interval of convergence is so important, because if you're writing a function that could calculate the natural logarithm for any input value, you would have to know that this one particular polynomial would work for values between 0 and 2. But if you needed other values of the natural log, you would need to come up with a new Taylor series centered at a different point so that you could, get a range of values outside of 0 to 2. So that's the importance of that convergence.